Somewhere between Jupiter's orbit and the scattered outer territories of the solar system, a visitor from another star is doing something it shouldn't be doing. Its name is 3 Atlas, and in the latest round of astrometric measurements, something has gone quietly, persistently wrong. When astronomers command their telescopes to point toward a predicted position, they expect to find the object within a narrow window, a few arc-seconds at most, a margin dictated by orbital mechanics and the precision of past observations. But 3I in Atlas isn't landing where the equations say it should. Night after night, across multiple instruments, from observatories scattered across continents, the residuals, the tiny differences between predicted and observed position, refuse to collapse. They remain coherent, directional, and stubbornly linked to time itself. This is not instrumental drift. This is not a catalog bias bleeding into the solution. This is the signature of something physical. The usual corrections have been applied. Teams have cross-checked star catalogs, accounted for atmospheric refraction, adjusted for timing errors that can creep into exposure windows. The mismatch remains. It is small, vanishingly small to anyone unfamiliar with the discipline of orbit determination. But in the language of celestial mechanics, it is a shout. And the most unsettling detail is this: the deviation appears real. But the obvious physical driver, the bright, dusty exhaust of outgassing that would push an object off its predicted path, is either faint, ambiguous, or missing entirely from the same observational window. If you're drawn to these kinds of mysteries, consider subscribing for more cosmic investigations from beyond the solar veil. The orbit solution has become a crime scene. Not in the sense of drama, but in the sense of method. Every number is evidence, every residual a clue. And the task now is to reconstruct what changed, when it began, and what the minimum defensible claim might be. In the weeks before the anomaly, the fit was stable. Observations fed into the ephemeris, the predicted sky position at any given time, and the object appeared where it was supposed to, within the noise floor of the measurements. Then, subtly, the residuals began to shift. Not randomly, but with a pattern. The best fit trajectory began to drift, as if the object were being nudged by a force not included in the gravitational model. Orbit determination is, at its core, a reverse engineering of invisible forces. Gravity from the sun, the planets, even the largest asteroids. These are always accounted for. But small accelerations, the kind produced by jets of gas venting into space, or the asymmetric reflection of sunlight off a spinning surface, accumulate over time into measurable sky-plane offsets. When multiple observatories, using different reduction pipelines, all report a consistent trend, the artifact hypothesis weakens. What remains is the possibility that the object is, in fact, pushing itself. The next step is to characterize the push. Is the deviation radial, aligned with the sun-object line, suggesting a force either toward or away from the sun? Is it transverse, running along the object's orbital track, as if something were accelerating or braking its motion? Or is it normal, perpendicular to the orbital plane, a force that would require a rotational asymmetry or a tilted active region? The direction of the acceleration is the first fingerprint. And in this case, the fingerprint is pointing in a direction that doesn't immediately resolve the mystery, it deepens it. Because when astronomers turn their instruments toward the task of finding the exhaust, the sky doesn't offer a simple answer. Photometry, the measurement of brightness over time, should reveal changes in reflected sunlight and scattered dust if a coma, a thin atmosphere of gas and particles, were present. Narrowband filters tuned to the emission lines of carbon monoxide, carbon dioxide, or water vapor should light up if those molecules are actively sublimating from the surface. Spectroscopy, the decomposition of light into its constituent wavelengths, should reveal the chemical fingerprints of outgassing in progress. These are the standard diagnostics, and they are routinely used to confirm cometary activity. But here, the picture is incomplete. There may be a weak coma, faint enough to evade detection in all but the most sensitive exposures, or directional enough to be hidden by geometry. Viewing angle matters enormously. An object can vent material in a tightly collimated jet, like a thruster firing from one side. And if that jet is pointed away from Earth or masked by the object's own body, the signature in our telescopes can be deceptively clean. The absence of obvious exhaust does not mean there is no exhaust. It may only mean we are not looking from the right angle, at the right wavelength, at the right moment in the object's rotation. And yet, the orbit solution suggests a push strong enough to accumulate into measurable positional error. If the non-gravitational acceleration is real, and if it is driven by outgassing, then why isn't the dust signature proportionally bright? Why isn't the coma unmistakable? Two possibilities emerge, both uncomfortable. Either the activity is unusually efficient, expelling mass in a way that maximizes thrust while minimizing observable scatter, or the mechanism is not the usual volatile story. Something else may be at work, something quieter, something less familiar. The investigation shifts, then, to a question of timing. Not what is pushing the object, but when the push appears, and whether that timing aligns with the physics we expect. As a comet or active asteroid approaches the Sun, solar heating increases. Surface ices begin to sublimate. Gas jets strengthen, carrying dust into space. The acceleration from this process should track insolation, the amount of solar energy hitting the surface, with a predictable delay as heat diffuses into subsurface layers and activates buried volatiles. This is the standard model, and it works remarkably well for most objects. But the latest move does not sit comfortably within that framework. The residuals appear to cluster in a window that doesn't neatly match the simplest thermal curve. The timing feels off, as if cause and effect have arrived in the wrong order. There are grounded explanations that can preserve realism. One is thermal wave lag, heat penetrating into deeper layers of porous, insulating material, reaching volatile-rich zones hours or even days after peak solar illumination. This can shift the timing of peak outgassing relative to the Sun object geometry, creating a phase offset in the observed acceleration. Another is seasonal illumination. If the object is spinning with a tilted axis, certain regions of the surface may only become fully exposed to sunlight at specific points in the orbit. A localized active region, perhaps a patch of exposed ice or a fissure venting from below, could turn on abruptly as it rotates into daylight, producing a sudden change in the non-gravitational force without a corresponding increase in overall coma brightness. A third possibility is structural. Cracking, shedding, or microfragmentation. Small bodies are not monolithic. They are aggregates, rubble piles, fractured shells held together by weak cohesion. As thermal stress builds, surfaces can crack open, exposing fresh volatiles to sunlight for the first time. A single shedding event, too small to produce a visible debris cloud, but large enough to change the object's reflective properties or vent a short-lived jet, could create a step function in the orbit solution, a discrete change rather than a smooth ramp. Scientists test these ideas by correlating residual growth with heliocentric distance, phase angle, and photometric modulation. They look for periodic signatures in the residuals that would match the object's rotation period. They search for brightness changes at optical wavelengths that would indicate fresh material, or asymmetries in the light curve that would suggest a non-uniform surface. The data may be telling us that the driver is real, but not synchronized the way intuition wants it to be. And then there is Jupiter. Not as a spectacle, not as a close encounter that warps the trajectory or tears the object apart, but as a quiet, persistent presence that alters the dynamical environment in subtle ways. Jupiter's gravitational influence matters, even when the object is far from a classical flyby. Small perturbations accumulate. Resonance-like sensitivities can amplify tiny forces, making them easier to detect or harder to model. The challenge of fitting an interstellar trajectory through a multi-body solar system is formidable, and even small errors in the assumed mass distribution or ephemeris of the giant planets can propagate into apparent anomalies in the residuals. But gravity is not the only environmental factor. The solar wind, the stream of charged particles flowing outward from the Sun, varies in intensity and structure with distance and solar activity. Magnetic fields thread through the heliosphere, twisting and reconnecting, shaping the behavior of ionized gas and charged dust. If 3I Atlas has even a weak coma, the interaction between that coma and the surrounding plasma environment can subtly reshape jet visibility, dust distribution, and even the force balance acting on the object. These effects are not exotic, they are standard physics, but they are messy, difficult to model precisely, and rarely the limiting factor for bright, active comets. For a faint marginal case like this, they may matter more than usual. Jupiter, then, is not a villain. It is an amplifier, a lens through which small, real physical processes become measurable at the edge of detection. The investigation has now reached a fork. Multiple explanations fit parts of the data. None fit all of it. And that is why the confusion persists. The first model family is familiar: non-gravitational acceleration driven by localized outgassing. Collimated jets, active at specific rotational phases. Seasonal illumination of volatile-rich patches. Changes in spin state, precession, or nutation that slowly reorient the active regions relative to the Sun. This model predicts specific signatures. Residuals should show periodic modulation, matching the rotation period. The coma, if detected, should exhibit asymmetry, brighter on one side or concentrated in a narrow fan. Photometry at different wavelengths should reveal subtle brightening in the ultraviolet or narrowband filters tuned to gas emission. If this model is correct, the next observing window should reveal these correlates. The second model family is structural. A minor fragmentation event. Shedding of surface material. A change in the object's area-to-mass ratio, which directly affects how strongly it responds to radiation pressure, the gentle but persistent push of sunlight itself. This model is capable of producing a step in the orbit solution, a discrete change in acceleration that appears suddenly, then stabilizes. It requires minimal gas detection, because the driver is not sublimation but geometry. If the object lost a small piece, or if its effective cross-section changed due to rotation or surface alteration, the radiation pressure term in the orbit fit would shift accordingly. This model predicts different signatures. No strong periodicity in the residuals, but a possible brightness change or color shift as fresh material is exposed. Spectroscopy might reveal dust, but not necessarily the molecular emission lines of active volatiles. The best teams are not choosing a story. They are choosing what the next data can falsify. They are identifying the measurements that will force one model or the other to fail. And they are honest about the fact that, for now, both remain uncomfortable, each explaining some of what is seen, neither explaining all of it. And so we return to the simplest truth. 3 Atlas is far away, faint, and moving through a solar system that constantly surprises us when we measure precisely enough. The latest move may turn out to be a normal process, wearing an unfamiliar mask. Geometry, timing, and weak activity conspiring to confuse even careful models. A subtle interplay of forces we understand individually, but struggle to predict in combination. Or it may reveal a boundary case. A hint of how interstellar objects behave when their histories were written under different stars, in different radiation environments with different volatile inventories. These objects are not merely distant, they are strangers. Their surfaces were shaped by stellar winds we will never observe, their interiors frozen under temperature regimes that do not match our own outer solar system. When they enter our domain and begin to warm, they may not respond the way our comets do. They may sublimate different molecules at different temperatures. They may fracture along planes of weakness that formed under alien thermal cycles. They may, in short, teach us that the rules we derive from studying our own population are more local than we assumed. Science does not rush to certainty in moments like this. It tightens questions until nature is forced to answer. It identifies the next critical measurement, the photometric light curve over a full rotation, the detection threshold for CO emission, the timing of residual growth relative to perihelion passage. It waits for the object to move into a more favorable viewing geometry, for larger telescopes to allocate time, for the data volume to grow beyond the point where ambiguity can hide. The most important discoveries often begin as a small mismatch no one can explain. A residual that won't go away, A fit that breaks when it shouldn't. A whisper in the data that refuses to be silenced by the usual corrections. 3 Atlas is whispering now, and we are listening. Whether the answer lies in a jet we cannot see, a fragment we have not yet isolated, or a dynamical coupling we are only beginning to model, the path forward is the same. Observe, measure, test, refine. Let the object move. Let the geometry change. Let the data accumulate until the pattern becomes undeniable. And in the quiet space between what we know and what we do not, allow the mystery to remain exactly what it is, an open question, a living investigation, and an invitation to keep watching the sky.